Right. We're happy to host Daniel Nakano, who will speak on realizing, in case you don't see it well, realizing rings of regular functions via the cohomology of one groups.
Yes. Thank you very much for the invitation to come to speak today at Northeastern. It's really been a pleasure being in Boston during this time. So what I'm going to do is I'm going to talk on work that took quite a bit of time to actually produce this preprint. It just appeared on the archive last October. It's with Zhongshu Lin, a collaborator I've been working with ever since the 1990s when we first graduated with our PhDs. So I'm not sure what number of papers we've had, but this is our latest. Okay, and this is dedicated to the memory of Georgia Benkart and Brian Parshall, two algebraists who passed away fairly recently. All right, so this talk will actually span a sort of long period of time. For some reason, I've been giving these historical talks recently. Maybe that's because I'm getting older. So this will actually span 5 decades of work. And so what I'm going to do is I'm going to sort of start with some problems that were introduced in this paper by Friedlander and Parshall, and also some computations done by them. And then I'll sort of move along the timeline as we go along during the talk. So there's a very important calculation by Ginsburg and Kumar, who calculated the cohomology for the quantum groups at the roots of unity. And that computation is very basic for this important paper by Arkhipov, Bezirkov, and Ginsburg. Maybe you've actually seen this paper before. I'll show you how this computation fits in here. And then we actually looked at this computation by Ginsburg and Kumar and generalized this for low roots of unity or small roots of unity. And then this is our current paper over here. And this is actually going to encompass a lot of the work, mostly in these 3 papers. All right. Now, I'd like to start out with a very basic problem for you. So let's start with a finite dimensional algebra. And what I want to do is I want to look at X between 2 modules. So just extension classes between a module and itself. And we can realize these extension classes by looking at these exact sequences over here. So they can be sort of represented by this S-fold exact sequence and this T-fold exact sequence over here. And now you can actually make the extensions between M and M into a ring. And all you do is you just concatenate these 2 together. So I just think of this M being identified with this M over here, and then you just push the sequences together. Actually, ironically, the ring structure is fairly easy to describe. The additive structure is actually harder to describe. Here's how the ring structure actually works. Right now, it's not known very much about this algebra. It's this algebra, the multiplication can be highly non-commutative, and there are very few examples in the literature which actually describe this structure. So, okay, but today we'll actually do a computation involving specific modules. Now, in order to do this, I have to start with the setting where there's more tools. Right, so I'm going to give you the standard Lie theoretic setting that maybe a lot of you are familiar with. So I'm going to work over an algebraically closed field K, characteristic P greater than 0. I'm going to work with a simply connected algebraic group. So if you want to think of SLN, you think of SLN with coefficients in K. T will be a maximal torus, maximal split torus. Whenever you have G and T, as maybe what you know, you can actually associate a root system to that. Okay, so that's going to be phi. Whenever you have a root system, you have a set of simple roots. H will be the Coxeter number, which is associated to this root system. So it's a number which is an invariant. So if you take the inner product of rho with alpha zero check plus one. So rho is going to have some positive roots, alpha zero is the highest short root. You take their inner product and then you add one, you get the Cox. The Borel subgroup I'm going to take is with respect to the negative roots. So this is the standard that's in Janssen's Representations of Algebraic Groups book. U is just the uniform radical of B. And whenever you're working in characteristic P, the Frobenius map is really important. So the Frobenius map gives you all the troubles, but it also gives you all the problems to work on. So here's the Frobenius map. So for GLM, it just takes a matrix entry and raises everything to the p power. G is the Lie algebra over here. And maybe you're not quite familiar with this, but this is what's called the restricted enveloping algebra, U of G. So this is a quotient of the ordinary universal enveloping algebra by an ideal which is generated by central elements. And so this algebra doesn't exist in characteristic zero, it exists in characteristic P. And the nice thing about this algebra is it's a finite dimension of the algebra. Okay, any questions on this slide? Good. All right, so just a little bit more sort of terminology. We have the dominant weights, which classify the irreducible representations. You also look at the p-restricted weights, which classify the representations for U of G, the irreducible representations for little U of G. And you want to classify the representations for the algebraic group over here, the simple modules, the co-standard modules, the standard modules, and the tilted modules are all indexed by dominant weights. Okay, so if you know things about quasi-hereditary algebras, the highest weight categories, these are fairly familiar players in the game. All right. So the next thing I'm going to do is I'm going to start out with the computation. So I said that the ring structure is really hard to compute for these algebras. So if you just take the trivial module K and K, you look at the X algebra for that. A long time ago, Anderson, Janssen, and Friedlander and Partial actually computed the exact structure of this. And there's a beautiful answer. And so, in geometric representation theory, you think, well, where does the nilpotent cone come into play? Well, it usually comes into play at the derived level. And we can see it right here. It's coming in as the cohomology of this algebra, which is the Lie algebra, related to the Lie algebra. All right. So basically, it says that the cohomology in odd degree vanishes. And the cohomology in even degree identifies with the coordinate algebra and the nilpotent cone, as long as P is bigger than the Cox. So N is the set of nilpotent elements inside of G. Okay, and we can actually compute what the ring structure is here. So it gives you an explicit ring structure for this kind of interesting X algebra. And so let's do an example of this. Like we're 2 by 2 trace zero matrices. Right? So if I look at nilpotent matrices, what's the condition that the matrix is nilpotent? Well, it's just that the determinant is actually equal to 0 in this case, right? So if you think of your matrix as being, let's see, Z and minus Z on the diagonal and X and Y on the off diagonals, then this is the determinant being 0 condition over here. And so this cohomology ring now identifies with this polynomial algebra modulo this relation. Okay, so if you actually try to compute this by hand, you could probably do it, but it would be kind of very difficult to actually just do this by hand. And if you can imagine like SL3, for example, it would be almost impossible to actually say that it's the coordinate algebra that nilpotent cone, right? So you're probably wondering, like, how this is actually done. how do you actually show that this abstract multiplication identifies with something so concrete like this, right? Okay, so normally,
So.
go ahead. Sure, go ahead.
So the degrees are spread out, so it's not the usual K of X, or is it? But
Yeah. This is a very excellent question. So it turns out that the degrees are in degree 2. Okay, that's what you show. Yes. So X, Y, and Z are all living in degree 2.
So can I ask a question? Yeah. So in characteristic 0, I mean, I guess you have the Chevalier-Eilenberg complex. So what you get for in characteristic 0, is that also related to the nilpotent cone in any way, or is it completely different?
It does, and you'll see this come up in the spectral sequence. So in characteristic 0, I'll show you later that the way you kind of realize the nilpotent cone is through the quantum group at a root of unity. And so there's going to be a theorem like this in characteristic 0, but you have to use a root of unity in order to get this.
Okay, cool.
Great, thanks. Okay, so normally I don't do this, but I wanted to sort of show you like how you actually prove this, how you actually prove that you get the nilpotent cone. And I think this argument is really beautiful. The way I think about this is the following. So what I'm going to do is I'm going to give you 3 spectral sequences. Okay. And I'm going to make every single spectral sequence collapse. Right. So when I make every single spectral sequence collapse, then out will come the answer. Okay. So that's the idea. So the tail of 3 spectral sequences collapse. That's kind of the theme of this. Okay, so the first thing I have to say is that there's a spectral sequence which actually converges to the cohomology over here. And this spectral sequence involves the induced module from B to G and its higher right derived functors. And so this spectral sequence is related to the geometry of the flag variety and its higher sheaf cohomologies. I'm not going to go through the construction, but there's something like this, right? So for the Borel, you have the cohomology for the Borel, and if you kind of know something about that, you can insert it and then see what happens. Right? So that's spectral sequence number 1. Okay, now spectral sequence number 2, you've probably seen before. If you have something which is normal inside of something else, just like with groups, then you have a Linden-Hochschilder spectral sequence like this, right? Now, it turns out that with the torus, all representations for U of T are completely reducible. Okay, so that means that fixed point functor is exact. So this spectral sequence will just collapse, right? So when it collapses, you can identify this cohomology here for B with the cohomology for U with the fixed points under T. Okay, so we have one down, one spectral sequence collapsed. Okay.
So maybe you can I ask you this?
Sure.
So RJ refers to the J right derived function
Yes.
of exactly what?
Oh, you mean, so this I up here or the J here? So this is the cohomology, the J cohomology. Okay, and Ri is the higher right derived functor, the I higher right derived functor of induction from B to
And
G.
what happens when when I equals 0?
When I is equal to 0, that's just the induction functor from B to G. I mean, it's just like when you take X, the 0, 1 is just a hump. So the functor is induction from B to G. It's left exact, and you have higher right derived. Does that make sense? You can also represent it. It's a representable functor too. Okay. All right. So 2 spectral sequences, 1 collapses. All right. Now, this spectral sequence is kind of important. So what you can do is you can filter the Kobar complex for the dual of the Lie algebra, or the dual of U of mu up here. And then this spectral sequence you could regrade to make it first quadrant. Now, this is what's called a May spectral sequence. And anybody who does like this or is interested in the finite generation problem for cohomology, this is where a lot of problems occur. Because like for higher Frobenius kernels, you can't write it as a first quadrant spectral sequence. So you don't have a lot of chances to have universal cycles that way, or construct universal cycles. But in this case, everything is nice. Everything's beautiful. So you have this nice first quadrant spectral sequence over here. And now you just apply the fixed point functor to everything. It's exact. So the fixed points act trivially here, and they act on the ordinary Lie algebra cohomology over here. And then they converge to the UB cohomology on this side. And now, because P is bigger than the Coxeter number, then it turns out that the cohomology over here only lives in degree 0. Okay, this is like the exterior algebra dual, and then you could just show that the fixed points under here are 0 unless J is equal to 0. Okay, so this spectral sequence now collapses. And so when you do that, so remember this is the old result. So all you get is the symmetric algebra here, polynomial algebra. Forget the twist. I mean, it's just a polynomial. Okay, so we have two spectral sequences collapsing, and now the B cohomology is computed as just the polynomial algebra. And note that the odd degree cohomology vanishes. Okay, so we're almost done. And now you reinsert the symmetric algebra into here. Okay, and then you use a theorem in characteristic 0, which is known as the Riemann-Schneider theorem. You have to do a little bit in characteristic P, but basically the answer is the same, is that the higher right-derived functors vanish when I is bigger than 0. Okay, so now this spectral sequence collapses. And you've now identified the cohomology here with an induced module from B to G on some polynomial algebra. Okay, and again, the odd degree cohomology vanishes. So we're almost there. We've actually identified the cohomology with a nice module. All right, so now you do some fun things. So maybe you've seen this before. This is called the Springer resolution. So this is a resolution of singularities for the nilpotent cone. So there's some basic facts. The nilpotent cone is a normal variety. It has singularities in codimension greater than or equal to 2. So we showed that the cohomology identifies with the induced module over here. It's an easy exercise to show that that's the same as the coordinate algebra on this orbit space. So this orbit space is smooth, right? It comes from there. And it turns out that the ring of regular functions identifies with the nilpotent cone because of the normality and the fact that the singularity is 9 codimensions greater than. And that finishes everything. So again, at the end, you use the nice little geometric argument to finish on the. Okay, any questions on this? Remember, 3 spectral sequences collapsing, and then use the geometric argument. Okay, good. So there's a lot of geometry involved here, and it turns out that you can sort of extend these arguments to modules which are not just the trivial module. So if you take the induced module over here, which I sort of described before, so you take induction from B to G of mu, where mu is a weight, then you get the global sections of the flag variety with this line bundle. When mu is equal to 0, you just get the trivial module again. And so this recovers the old result. And it turns out that you can express this as an induced module and then tensored by some weight over here. Okay. And what else can we say? Well, this is a module for coordinate algebra of the nilpotent cone. And so one way to think about this is actually sheep for the notebook. All right, and the proof is really similar to what I described before, except you have to work a little bit harder with the Broward, Riemann, Schneider. Okay. All right, so now, so back in 1986, Friedlander and Partial asked the following question. So suppose you take a subset of simple roots, and you take the parabolic associated with that, and you take its unipotent radical. And what I can do is I can take this unipotent radical and I can saturate it with the action at G. This is an irreducible set, turns out. It's closed because of the completeness of G mod P. And it turns out that this is actually the closure of an orbit. And these orbits are called Richardson orbits. So maybe many of you know that for the nilpotent cone, there are only finitely many orbits. Now, not every orbit is Richardson, but in type A, every orbit can be sort of written in this. In type B, C, D, E6, E7, there are non-Richardson orbits. Okay, so these are particular orbit closures. And so their question was the following. So you suppose you take the coordinate algebra of an orbit closure. Okay, so the nilpotent cone is the closure of the regular orbit. So you take its coordinate algebra. Can you actually find an algebra A for which the cohomology is actually equal to that coordinate algebra? So that's the Friedlander question. So the realization of the coordinate algebra of orbit closures via the cohomology for the restricted interval.
Those areas with subrise have to do with partitions. The orbits.
In type A for sure. And I'll actually mention this in a second, how the correspondence goes. You have to take what you have to do is you have to take the partition, you have to take its transposed. And then what you do is you sort of look at the Levy, the Dinkin diagram, with that partition and transpose. That's how you get the UJ. Okay. So we'll go over that. That's good. Good. Very good. Okay. So this was an open problem for a while. All right, so what I'd like to do is now switch the quantum world. So I described the case in characteristic P because the proofs are easier in that case. For the quantum groups, you have to work harder, but everything is somewhat analogous. The advantage with quantum groups is you're working over the complex numbers. So you have more complex algebraic geometry that you can actually use with more tools in your bag. All right, so this U zeta G is similar to the restricted envelopment algebra. Okay, so this is the analog. The small quantum group is the analog to the restricted envelopment algebra. This DeConcini-Katz quantum algebra is analogous to the universal enveloping algebra. So this is a quotient of the DeConcini-Katz quantum algebra. And this listed quantum algebra is the analog to what's called the distribution algebra. So it turns out that the small quantum group is a subalgebra of the listed quantum algebra. And the characteristic P is replaced by looking at a certain root of unity inside the complex numbers and specializing these algebras at certain roots of unity. Okay. And just like with the reductive case, the players are kind of the same. You have these induced modules, you have the file modules, you have the tilting modules, you have the irreducibles, blah, 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 blah. So that part's kind of analogous. Now, what is not analogous is the following fact. So if you take a normal, so this thing is actually a normal sub-Hopf algebra inside this listed quantum algebra. Okay. And so the question is, what happens when you take a quotient of this small quantum group inside of here? And when you take a quotient, then you think, oh, maybe I get something quantum again. But the answer is no. The answer is you get something which is not quantum. So when you take the quotient over here, you get the ordinary universal enveloping algebra back again. So what that says is that you can only iterate Frobenius one time. Whereas in the reductive group case, you can continually iterate Frobenius, right? So with the quantum group situation, it's an easier model in terms of representation theory because of this fact. This is why, like, Lustig's conjecture is true for quantum groups, for example, and it's like not true for reductive groups. This is like the big reason why is because you can only iterate Frobenius one, and then you're out of the quantum world, you're into the ordinary complex Lie theory. Okay. All right. Okay, so you have an analogous theorem for quantum groups. So I presented the one for the restricted enveloping algebra. The statement's basically the same. As long as the root of unity has order bigger than h, then you get the same answer. Okay, so the cohomology of the small quantum group is the coordinate algebra on the nilpotent cone. Ordinary cohomology is 0. And when Ginsburg and Kumar proved this, they created what was called the naive function. So basically, the idea is that when you plug in a module over here, a module for the big distribution algebra, then this actually becomes a G module. And so this is a coherent sheaf over the nilpotent cone. Okay, so this is a way to actually produce coherent sheaves over the nilpotent. And this will come up in a moment. Actually, it's going to come up right now. Okay, so so for people who are familiar with a little bit of geometric representation theory, this turns out to be a very, very important and fundamental paper. So the reason why I think it's fundamental is because it relates coherent sheaves with perverse sheaves with also the category of modules for the quantum group. So they proved that there's an equivalence of these derived categories. And this is like the principal block for the big quantum group that I mentioned, the Lustig form. But then you have to do some technical things to this. This is the G-equivariant coherent sheaves on the Springer resolution. And then you have to put this additional C-star action on this. And when you take the Langland's dual group and you take the loop Grossmannian on this, you look at perverse sheaves on this. And they show that there's an equivalence of categories on the derived level. And one of the things they had to do was they had to, and this is explained in their paper, is they had to take that naive functor and they had to lift it to the derived level. So built into this picture is that naive functor that I mentioned before. And moreover, how do you sort of get this answer over here in terms of the Springer resolution? It turns out on the level of cohomologies, that's where the cohomological calculation comes into play. Okay, so the cohomology of the quantum group or small quantum group definitely plays a role in this theorem. Okay, so I'll just briefly say that this theorem has been used for a lot of things. You can prove the Lustig character formula with this theorem. There was an earlier version that was due to Kashina Lustig and Kashiwara Tanasaki. So this is like second generation proof. And then it turns out that when you look at the X groups between two irreducible modules with regular highest weight, you can actually do a computation there. The dimensions of these are given by Cauchy-Lustig polynomials. And then Bezer-Kovnikov used this to actually compute support varieties for tilting modules too. Okay, so this actually answers the Humphreys conjecture in quantum physics. Okay. All right, so before I start, this is sort of what I want to do for the last part of the talk is I gave you a lot of computations. Okay, and what I'd like to do is I'd like to present a way, or a sort of axiomatic way, to get all these computations under one umbrella. Right, so I'm gonna present what I call the meta theorem, which allows you to, say things, and then when you specialize various parameters over here, then you get the results that we know and some results that we don't know. Okay. All right, so all this looks like it's technical, but I'm just going to point out a few things that you've actually seen before. All right, so first of all, don't worry so much about the notation and things. So the ZJ over here is just an ideal of central elements. Okay, so they're defined by these FIs to the power L or something. And you want those things to just annihilate your module. Okay. And then you want a module for the parabolic over here, and you want to have these sort of conditions being true. This condition here is very much like the condition that I explained back in the proof, where you take the exterior algebra or the cohomology for U of U, and you apply the fixed points under T, and then you get things just living at degree 0. Okay, so this sort of says that when you take this Hom over here, elements are only going to live in 1 degree. Okay, so that's kind of the analog of that. And this condition here is like this Grauer-Riemann-Schneider, vanishing. The higher sheaf cohomologies vanish. Okay, so the Friedlander partial proof, the elements are sort of built into some of these axioms. Now, once you have all of this, then you can actually prove a theorem. So you have all these conditions being true, and then you create this module N over here. And then you can actually compute the cohomology for this thing. And it kind of looks familiar. It looks like the coordinate algebra of the nilpotent cone, maybe twisted by a weight or something. Okay, so under these conditions, you can actually compute cohomology like this. And as you can imagine, you've seen what goes into this kind of theorem: spectral sequences, weight combinatorics, and this Grauer-Riemann-Schneider vanishing. Okay. But you have to use much more like involved techniques. Okay. The ideas are kind of the same, but the technical details are more important. Okay, so the cool thing about this is now you can specialize some of this. So if you specialize the main theorem where J is the empty set, W is the identity, gamma is 0, M is the trivial module, Q is the trivial module. All right. So you specialize all these modules and all these like elements, then you get Ginsburg-Kumar out again. This pops right up. And as we know, we've done this before, right? We've identified this induced module with the coordinate algebra. We went over that argument before. Okay, let me stop. Any questions on this so far? We have this big meta theorem and we're just specializing.
Yeah, I had a question. Where in your conditions, like 1 through 4, so in other points you wanted to say like the prime was bigger than the Coxeter number. Is that?
It's
Or sorry, like your root of unity. Like where does the
it's
precise
number 3. Number 3 is 3 because it's exactly the same step as when we took the cohomology and we applied the T fixed points or the U of T fixed points, and we said that only lives in degree 0 for in the Friedlander partial proof. And so this is where your root of unity is bigger than the Coxeter.
Okay.
For 3. So
Is this the sort of thing? Is 3 the sort of thing that's, well, maybe, yeah. Okay, never mind. That answers my question.
you use the root combination in 3 with L being bigger than 8. That's the,
Oh, okay, thanks.
it's a good question. So that's where it comes in. Okay. And so now I could specialize in a different way and answer the Friedlander partial question. So this time I'm going to take W to be the identity. I'm going to take these partial Steinberg modules. So what I do is I take fundamental, I take dominant weights, fundamental dominant weights, and I just look at things only on J. Okay, and so I take like something which looks like the Steinberg, but it has zeros in places where you're not on J. So this is called a partial Steinberg, and you take this thing and you take its dual, and here's the Q over here. And when you specialize this, you get this theorem over here. And so if you take a Richardson orbit and you have this moment map. Now, this may not be a resolution of singularities. All right, so we have to be a little bit careful. It might not be 1-to-1 unless the centralizer of the orbit is connected. So then you create a algebra A of O, which is related to these partial Steinberg modules, and you do the same sort of deal. You apply this meta theorem, and the odd degree cohomology vanishes, and the even degree cohomology identifies with this polynomial algebra, which you have to induce from PJ up to G. Okay. Now, if you have the additional conditions involving a resolution of singularities over here, and the normality of this orbit closure, then you can actually answer the Friedlander partial question. Okay, but you need the geometric conditions to actually answer their question fully. Okay. But at least you can say that it's going to be the coordinate algebra on this orbit space. Okay, so now in type A, things become very clean. So I think this will answer your question. So I just did this to be kind of down to earth. So you take GLN, L is bigger than M, so N's a Cox number, and you take a partition of that. And then you just take the dual partition over here, take the transpose partition, and you take the subset of simple roots corresponding to this partition. So the way to think about it is you have this partition, you take the Dinkin diagram, and then you have the parts, and you just take the parts, the number of parts plus 1 on the components of the Dinkin diagram. That will give you your U of J over here. And because the centralizers of nilpotent elements under GLN are connected for nilpotent elements, and it turns out that this moment map is always a desingularization. And then from work with Kraft and Cortese, all G-orbit closures are nilpotent, or sort of normal. And then so everything works out. So type A, you can answer the Friedlander partial question completely. Okay.
Right.
Yeah.
Do we know explicit like definition or how we construct the A, the algebra A?
Oh, that's going to come up in a second. That's a really good question. All right, so I'm gonna go over that in a moment. Okay. Good. Yeah, the answer is yes, absolutely. Right. Now, yeah, so in type A, you can answer this, and also for the restricted enveloping algebra, you could just do the same thing. Okay, so I stated this for the quantum case, but for the restricted enveloping algebra, it just follows in the same way. Okay, so you can just use, and you have to check certain conditions, but everything works out. Okay, so now I'm going to answer your question. Very good question. So back to the Yoneda algebra, Yoneda product. So what you do is you take a subset of simple roots, right? And how do you realize this A of O? Well, you realize that the endomorphism algebra on the Steinberg module, partial Steinberg module. So A of O, you're going to take the dual here tensor this, which is the same as endomorphism algebra. And then by the realization theorem, that we had before, the odd degree cohomology vanishes for this. So this is your M and your M. And here, your X algebra is the coordinate algebra on this orbit space. Now, this space here is the commutative algebra. And so, I don't know, I'm not sure if it's surprising or not that this is actually a commutative algebra or not. That's a mystery to us, you know, why it's actually a commutative algebra. It would be interesting to do other examples of this. And maybe in this, I don't know, maybe in this case, it would be kind of a wild dream. Maybe all the X algebras or finite dimensional models are commutative. I don't know. But this is just like the tip of the iceberg right now. Okay. All right. Okay, so a few more things. It turns out that you can actually generalize Ginsburg and Kumar's computation by using tilting modules, which are related to these partial Steinberg modules. So this is rather kind of technical, but it turns out that you can look at tilting modules for the Levy subalgebra, and you can actually realize these tilting modules when I take these particular weights as a summand inside of this tensor product over here. Okay. So this goes back to work of Cornelius Pillen in terms of realizing certain tilting modules for projective indecomposable modules for the first Frobenius kernel inside a tensor product like this. Okay. All right. So then again, you can prove a theorem involving the induced modules on this tilting module. Again, this answer is kind of the same all the time, right? And so the techniques are kind of the same as what I introduced earlier. And the interesting thing about this computation is that we don't know the dimension of the tilting modules at all, but we do know the cohomology. Okay, so we don't know the dimensions of these TJs, but yet we can still compute the cohomology. And that turns out to be kind of a powerful idea. And when you take this theorem and you specialize, again, you specialize all these parameters up here, then you get something which looks like the the Kumar-Lorenzen-Thompson result that I presented earlier. So you can compute the cohomology of the induced modules, and you get a similar result as what Kumar-Lorenzen-Thompson did for reductive algebraic groups. As far as I know, this was not known before. Okay, so this is kind of a new result that comes out just from the meta theorem that I presented before. Okay, great. All right, so I want to finish off by kind of giving you a sort of general philosophy or general principle. So it turns out that when you create this module that I had before in the theorem, and you want to look at the number of times this composition factor appears in this G module over here, then it turns out that you can compute this by computing an X in the category of modules for the quantum group. Now, as you know, if you take modules for like GLN over the complex numbers, you know, these are completely reducible. So on the left-hand side, you have things which are completely reducible, and their composition factor multiplicities are given by dimensions of extension groups in a world where you have non-semi-simplicity. All right, so many people actually work in these worlds. I mean, many people work in the world of complex algebraic geometry. You know, they study like Schubert varieties, Springer fibers, flag varieties, nilpotent cone. And I just want to warn you, make people aware that there is the dark world of quantum loops behind the scenes. You know, the dark underworld of quantum loops. So whenever you're actually doing these kind of computations, there's a quantum group behind this, which is actually telling you something about composition multiplicities. And I don't think this has been exploited that fully yet. Okay, so it would be really interesting to sort of make these connections between like the complex Lie theory world and the derived world involving quantum groups. Okay, so that's where I want to stop the talk. And again, thank you for your attention.
Any questions from the Zoom audience?
Oh, I should mention the picture here.
Yeah.
So, Lustig's 60th birthday conference was in 2006 at MIT. And Zhongxi Lin is to the left of me over here. And these were, I think they were mostly graduate students at that time. And they wanted to see George Lustig's office. So Jordan was kind enough to actually show us like his office at MIT. This is a picture from that con.
He doesn't look happy about it.
Yes, I think it was pretty happy at the birthday con.
Any questions from the audience here? I wanted to ask why the world of quantum groups is darker.
Well, it's kind of hidden, right? I mean, it's something which, so let me go back a little bit. So it's just something which is kind of hidden and mysterious. I guess that's the way I more or less present this. People just don't know very much about this. There's been so much work done in terms of this side over here, you know, combinatorics and, you know, partition functions. And people have sort of ignored the fact that there's this connection, definite connection between the two.
I wanted to ask another question. So if the first was a question.
Okay.
So you said that for some modules,
Yeah.
you compute the X groups and becomes commutative.
Yeah.
Can you see the commutativity without doing all possible spectral sequences and getting explicitly the final result? Is there like a method that you can use to show directly that the X is commutative?
You know, I
Where do you
don't
see that?
actually, that's a really good, I don't know the answer to that. I mean, it would be interesting to do other computations and whether you can piece together those other computations to figure out whether it is commutative or not. Usually, you know, people would highly suspect it's not commutative. But there have been so few computations, you know, in this direction that we just don't know. I mean, maybe some of the finite dimensional algebra people have actually done more. But it's really hard unless you have tools. And since we're working with quantum groups and Lie theory, we have all these spectral sequence tools.
Because if you're like saying the world of tensor categories, categories, then the X of the identity is commutative by a simple argument.
Yeah, that's right.
And I would assume that maybe X of some algebra in that category is commutative by a single argument. So possibly here the commutativity comes from some property of this module being something in that category, not just a module.
Yeah, I think that's a really great question. I just don't think we have the technology. But it would be really interesting to understand these X morphologies.
Yeah, I have a comment for this commutativity. So, yeah, I'm not expert in that direction, but I seem to remember when people study Coulomb branch, even varieties, they also have this commutative algebra that arises from calculating geometry and cohomology rings.
Oh, interesting.
And that part, plurality is a kind of analog on this nickel resolution of nickel cone. So we share, I guess we share many scales.
It is actually the X algebra of an algebra in a network.
Yeah, go ahead, Ken.
Is any of this story done in first super groups?
That's, again, that's a really good, so I actually asked Christopher Bresky about this. He and John Cordella are working really hard on this. And there are very few computations in this regard. So if you take like characteristic P, GL, you could define this sort of restricted also. And it turns out that the cohomology here is not that. So for ordinary GLN, it is, but for super, the general linearly super algebra is restricted. And part of it is that there's not a good theory of the induction functor yet. Okay, we're hoping that maybe with BBW parabolics, that would definitely help. But, it's still not known how to induce in an appropriate way.
Any other questions?
Yeah, I had a question. So in this correspondence, I forget the 3-letter, the initials, but the correspondence you mentioned, like the derived category of representations of the big quantum group is equivalent to some other stuff. Yes. So if I replace the big quantum group here with the small quantum group, does the thing in the middle become coherent sheaves on the null cone? Or
I'm actually sure. This is, I'm not sure. There's a lot of like really subtle issues, I think, that they had to actually deal with. And so this was the I guess maybe the cleanest way to actually state this equivalence. You may be able to tweak it some, but I'm not an expert on this in terms of the technicalities.
okay. But then the thing in the middle is not the null cone, it's the Springer resolution, or you said that
Springer resolution, yes, absolutely.
okay, cool. Awesome, thanks.
Any other questions? Let's thank them for the wonderful talk.
Oh, yes, no problem. The one house.